Hello again. So the last lecture, we basically just defined music, tried to come up with a definition of what is music. And we agreed, at least I agreed, that the definition we're going to use anyway, like if it was a question on a test, would be that music is the art of organizing sounds in time. And that definition has all the basic elements, but it doesn't have anything that would exclude. So for example, if you talk about melody, that music has to have melody. No, actually music doesn't have to have melody. It doesn't have to have instruments. It doesn't have to have voices. It doesn't really have to have harmony, or a lot of the things that we associate with music don't have to be there. Now, most music may have those things, but it doesn't have to have them in order to be considered music. So a good definition, remember, includes only those things that are absolutely necessary and not anything that is extra, or that if it didn't have those things, we couldn't call it music. Right? And so music is the art of organizing sounds in time. And I also made the point that the in time part at the end of that definition is kind of important, because one of the most fundamental things about music is that it exists in time and not in space. And every single thing that you can think about in terms of music really is a manifestation of time rather than space. And I'm going to start talking about what that means exactly. Right? It has to do with the nature of sound. Where the book goes from where we just left off is in talking about qualities of sound. And I'm just here on page 4, part 1, chapter 1. It says sound, pitch, dynamics, and tone color. It says here, sound begins with the vibration of an object, such as a table that is pounded or a string that is plucked. The vibrations are transmitted to our ears by a medium, which is usually air. Right? And we all probably knew this, that sound is caused by vibration. But they are not exactly the same thing. And this is what leads me to address that age-old question. If a tree falls in the forest and no one is there to hear it, does it make a sound? And I would argue that no, it doesn't make a sound. It makes vibrations, but sound and vibrations are not the exact same thing. Sound is caused by vibrations, but sound is the sense that your brain makes of vibrations. Okay, and it might seem like splitting hairs to make such a fine point of it, but that's what we do when we are learning and trying to come up with good definitions. Sound is caused by vibrations, but not all vibrations will result in a sound. It depends on your hearing range. So, for example, vibrations at 40,000 cycles per second, you might not hear, but a dog or a cat will hear. Right? So, now, sound begins with vibrations. So what we need to do is start classifying different types of vibrations, because that's going to give us different types of sounds. Right? Vibrations can either be regular or irregular. What do I mean by regular? Well, meaning that they are at some steady speed, which we could measure. Right? If those vibrations, like any kind of vibration, if they're happening at a steady rate, like let's say 50 times per second, right? That's going to correspond to a certain tone, which we could also call a pitch. Now, the word pitch, sometimes used as a noun and sometimes used as an adjective, but a tone is a sound which has a certain pitch because it is produced by regular vibrations. Right? So, for example, on this piano behind me, there's a particular key which we use to tune up if we're playing in an orchestra. This is the A above middle C on the piano, and it's sometimes known as A440 because what you are hearing is the air in this room actually transmitted through the interwebs and out your phone. So the air in the room you're in, or your laptop, whatever it is vibrating. And it's vibrating 440 times back and forth every single second. We call that A440. 440 vibrations per second, or beats per second, or cycles per second. All mean the same thing. We also might call it 440 hertz. Herz. It's the name of the scientist who studied sound, and so his name is given to this measurement of cycles per second, and it's abbreviated Hz. So this particular pitch, A above middle C on the piano, 440 hertz. And now, obviously, all the other keys on the piano also had their own number. But each one of them, we could say, is a tone. It has a certain pitch, and the reason is that the vibrations are happening at a regular rate that we could measure. We could have a sophisticated piece of equipment in here to measure exactly what that rate is. There are other types of sounds that are created by irregular vibrations, right? And it's not exactly cut and dried, actually. Sound is such an incredibly complex thing. That there's sort of a spectrum, actually, of more regular or more ordered vibrations and less ordered, disordered vibrations. Generally, the sounds that are less ordered, where the vibrations are less regular, let's say that maybe the rate of vibration is changing all the time, and we can't get a fix on it. It's not at one certain number. Or let's say that there are so many different vibrations going on at the same time that we can't get a fix on any one individual pitch. There could be a lot of reasons for it, but generally if we have disordered, irregular vibrations, we call that noise, right? And so pitches or tones are caused by regular vibrations, and noise is caused by irregular vibrations. And again, that's a sort of a simplistic way of dealing with it, but we could actually teach an entire course just on sound because it's such a complex thing. It's a thing we take for granted because we just hear sounds and we don't think about it every day. But once you study this issue, it's incredibly complex, the way that things vibrate and the sounds that they make. Now, noise sometimes sounds like a judgment or a condemnation. Like if your parents say, "Will you turn down that noise?" Noise, it's not necessarily a bad thing. It's not like music is pleasant sounds and noise are unpleasant sounds. I want you to get that idea right out of your head, because for one thing, you can make music using noise. It could be made entirely of noise, or there could be some noise in there and some tones. Noise is sound. And so thinking back to our definition of music, you could use noises rather than tones as long as you are ordering or organizing those sounds and you're making an attempt to be artistic, then that could count as music, right? So noise can definitely be used in music, even in classical music, because, for example, a lot of the percussion instruments technically produce noises, things like drums and cymbals, that are not producing tones or pitches, produce noises. Now, there are other kinds of drums that do produce tones, right? And when we get to talking about the different types of instruments, we will classify the percussion instruments into those that produce tones or pitches and those that tend to produce more noises, right? But they are all musical instruments, and they are all perfectly useful for creating music. So noise does not mean bad, right? Okay. However, if we're going to start talking about sound that is used for music, it's probably more useful that we're going to talk more about tones and pitches, right? There's just kind of less to talk about in terms of noises, because noises is just a big category of disordered vibrations. Let's talk about the other side, about ordered vibrations or regular vibrations. So I've already said we measure these vibrations in terms of their cycles per second. So a cycle, think of a thing that's vibrating up and down, right? One time up and down is a cycle. Um, and what we're talking about also is waves. Okay, sound, as you probably know, sound is a wave phenomenon. But you shouldn't really think of it as an up and down. Actually, we tend to think of it that way. We tend to think of, for example, waves on the ocean. We see waves on the ocean. We see the water go up and down. If you go to a stadium and you see people doing the wave, what happens is a bunch of people stand up and sit down and synchronize. And that's actually a very useful way of visualizing waves. That's not exactly how sound waves work, though. It's similar but different. Okay? When you think about a wave going around a stadium, the people doing the wave are standing up and sitting back down again in one dimension, right? The up and down dimension. And the wave is traveling perpendicular to that in another direction. And keep in mind, it's not the people that are moving in that direction. The wave is moving in that direction, but the people are moving up and down, right? So the people and the wave are not moving in the same way, right? Same thing, by the way, waves on the ocean. The individual water molecules in an ocean wave are going up and down. They might be making sort of a little bit of an oval shape. They're going up and down, but as they go up and then back down, the wave is going this way, right? It's going at a 90-degree angle and traveling across the surface of the water. Right? Sound waves are different, though, because what a sound wave is, it's a pressure wave moving through the air in 3 dimensions. It starts from the source, right? The source vibrates, and then what that does is it pushes the air molecules around it. And what you have are areas where the air molecules are compressed, are closer together, and then areas in between where the air molecules are farther apart, what we call rarefied air molecules versus compressed air molecules. And it's not really the air molecules that are moving all that much. It's the wave that is moving as regions of air become more compressed or more spread apart. It's interesting because this kind of relates to our pandemic, right? And, everyone's wearing masks, of course, and there have been some concerns about wind instruments. In fact, I happen to know a friend of my son who is in the Penn State Blue Band, and he and his fellow bandmates have been told that they have to play their tubas and trumpets and whatever with a cover over top of them so that the air coming out of the instrument is not infected with the virus. And this betrays a total ignorance of how wind instruments work, right? There is very, very little air coming out of the end of a trumpet. You see a guy playing a trumpet and he looks like he's blowing to the thing for all he's worth. But there is so little air coming out of that trumpet that you could hold the trumpet up to a candle and not put it out, right? So you need not fear the coronavirus vaccine coming flying out of a trumpet or a tuba, because that's not how it works. It's not air coming out of the trumpet. It's a sound wave coming out of the trumpet. The air and the wave are not the same thing, just like in the stadium. The people and the wave are not the same thing. The people are a medium through which the wave travels. So that's what they're talking about in here. A medium is something that carries a wave. You could think of it also another way. Like you've got, in the old days of telephone wires, you've got a telephone wire, right? That's the medium. It's not the same thing as the phone call, right? Okay. So, sound is a wave phenomenon, and you've got a pressure wave that is traveling through the air. And by the way, that's why in space nobody can hear you scream, because there's no air in space. There's no sound in space. People who know about how sound works, it really bugs us when we go to the movies and this big spaceship flies by and you hear this sound. It doesn't work like that. There's no sound in space because there's no air to carry the sound. There's no medium there. right, to carry the sound. Now, let's talk a little bit about pitch, what the book calls the highness or lowness of sound. And I'll probably only have time to talk about pitch today. I'll talk about volume or dynamics. Dynamics is just kind of like the fancy classical word for volume. Today I'm just going to talk about pitch. Okay? Now, first of all, right off the bat, there's a big kind of an error in here in the way that we think about pitch. It says pitch, highness or lowness of sound. But remember, we've already said music is something, and sound really, is something that does not exist in space. It exists in time. There is no highness or lowness to a pitch. High pitches are not up there somewhere, and low pitches are not down there somewhere. Right? The problem is that we are such visual creatures, right? We get so much information visually that we tend to think of everything in terms of visual and spatial terms rather than in auditory or temporal terms. Temporal means having to do with time. And music and sound is a phenomenon that is almost exclusively within the world of time and not within the world of space. What do I mean by that? What I mean is the highest note on this piano, now it's the highest. See, I can't even avoid using that word because that's the word that you understand. It's the highest, but it's not up there. Now, it is a little bit more over to the right on this piano, whereas the lowest note is over to the left. But they could have made the piano the other way, right? They could have made it so that the highest note was more to the left and the lowest note was more to the right. That's more just a quirk of the machine that we are using to make the sound. High sounds are not up high somewhere and low sounds are not down low somewhere. It has nothing to do with space. High and low are terms that have to do with space, and there's nothing having to do with space really going on here. What high sounds are, it means high frequency. Again, high is the wrong word. It means that a thing is vibrating more frequently in time, whereas a lower sound, a lower pitch, corresponds to or is caused by a thing that is vibrating less frequently in time, right? You've probably heard this word frequency as applied to wave phenomena, right? All waves have what we call an amplitude and a frequency. I'm going to talk more about amplitude next time, but basically the amplitude is the amount of energy in the wave, the size of the wave. Think of waves on the water. Again, you can have little ripples, or you can have a tidal wave, a tsunami, and you can have everything in between, right? Big waves, small waves. That's the amplitude of a wave, the amount of energy it has, right? A big wave will knock you right over. A little wave you might not even notice. And that's a completely separate issue from the frequency of the wave. The frequency is a question of how many times in a given period of time do we see waves coming in, or do we see the waves occurring, or do we hear the waves occurring, right? You could stand there at the beach with a stopwatch and measure how frequently the waves are coming in. That would be the frequency. That's a completely different issue from how big the waves are, right? That is amplitude. So when we're talking about the pitch, the quote-unquote highness or lowness of sound, what we are really talking about is its frequency, and that is how frequently in time are those waves occurring. And that's where we use the measurement hertz, or cycles per second. Right? Now, I already pointed out one pitch in particular on the piano, the note that we tuned to A440. And that's A440 because it's 440 cycles per second. Now, this is a little preview of something I'm going to talk about in a future lecture. This is what's one of the things that's difficult about music. It's difficult to talk about any one aspect at a time because they're all interrelated, right? Ideally, I would be able to talk about many different things at once, but I can't do that. I'm limited. I can only talk about one thing at a time in a continuous stream. But here's a preview of something that we'll talk about later. You might be aware there are many different notes that we could call A on the piano, and they are in different octaves, right? Here's one A, A440. Here is A an octave below. And if I could tilt my camera a little bit, you would see that the positioning of the key is just the same. It's just the next A down, right? Here was the A that I touched first. And here's the next A down. And again, I use the word down. I could have used the word to the left. The space doesn't really matter. It's the frequency. Here's the next A down. And each time you can hear that it's like the same pitch but lower. And it turns out the very lowest note on the piano is also an A. Now, here's the interesting thing. As I go down and play each of those A's, what I'm really doing, I'm not going lower. I'm not going anywhere in space. All I'm doing is I'm cutting the frequency in half, exactly in half. So this is A440. This is A220. This is A110. This is A55. And this A is about 27 and a half. And that's as low as the piano goes. Well, why not go lower? Because the lower you go, you start to run up against the human ears and the human brain's limitations on detecting or making sense of frequencies. And you're all aware that different animals have different capabilities in detecting pitches. For example, you know that dogs can hear much higher frequencies than humans. Cats can as well. Mice. In fact, one of the ways that dogs and cats can catch mice is not necessarily by seeing them, certainly, or not even by smelling them. They can hear them because mice communicate to each other in frequencies that people cannot hear, but cats can hear. And then there are other animals that, insects that communicate at even higher frequencies. There are certain animals like whales and elephants that communicate in frequencies that create pitches that are too low for us to detect. Right? The human hearing range is, and it depends a little bit on your age because of the way the ears work. I'll talk about this in a second as well. The human hearing range is roughly something like 20 cycles per second, up to around 20 or 30,000. Okay, now 20 cycles per second, that's 20 vibrations every second. Now, you can hear sounds below that, but it's not going to coalesce and form a pitch. It's going to sound like a series of thumps. It's just going to feel like vibrations, but not really a sound. Right? Once you get above 20 or 30 cycles per second, what happens is your eardrum cannot keep up with those frequencies. Right? Here's how hearing works. The air vibrates, right? Like let's say I press that key on the piano, and what's happening inside the piano is a little felt-tipped hammer comes up and hits some strings. Those strings vibrate. The vibration of those strings is transferred via something called a bridge to the soundboard of the piano. The soundboard of the piano is a big piece of spruce, a big piece of wood, and that's basically like the speaker of the piano. Because the strings themselves aren't nearly powerful enough to cause very much air to vibrate. Those vibrations of the strings have to be amplified with a sort of a speaker. Same way on a guitar, by the way. The body of the guitar is the speaker. And if you've noticed, an electric guitar that is not plugged in doesn't make very much sound at all because it's not meant to. The body of the guitar is pretty much just something to hold on to, right? Whereas in an acoustic guitar, the body of the guitar is the speaker. Okay, so the sound is transferred via some kind of a speaker to the air, and the air starts vibrating back and forth. And this pressure wave moves through the air, and it actually moves through the air into your ears. And that air pushes on your eardrums and causes your eardrums to vibrate back and forth. At whatever speed, the air is vibrating. So if I push down this key, not only is the strings and the soundboard of the piano and the air in the room vibrating back and forth 440 times every second, my eardrum is vibrating back and forth 440 times every second. And then that is turned into sort of an electronic signal that goes through my auditory nerve to my brain. And that's where the sound really is. That's where my brain says, aha, that's A440, right? But if your eardrum can't keep up, if your eardrum can't vibrate that fast, you're not going to hear that sound. So the human eardrum is a certain size. It isn't small enough to vibrate back and forth at, let's say, 50,000 cycles per second. Right? A cat's eardrum, a dog's eardrum is capable of doing that. The human eardrum is not. And furthermore, as you get older, one of the reasons that older people start to lose their hearing, especially they start to lose the higher frequencies, is because the cartilage that forms their eardrum starts to get kind of old and hard, and the eardrum can't vibrate as fast anymore. It can't keep up with those higher frequencies, and everything starts to sound probably kind of like dull, like you're underwater. And so the older you are, the harder time you have hearing higher frequency sounds. Right? So we've talked about quite a bit of stuff here. And again, I've got to wrap up my video fairly soon if I'm going to have any hope of uploading the thing. So pitches, to review, are sounds, pitches or tones, kind of an interchangeable term, are sounds that are caused by regular vibrations occurring at a certain speed, which we could measure. It's cycles per second or hertz, right? The octave is a particularly important quote-unquote distance. It's not really a distance. It's a difference between two pitches. It's a difference in frequency. What the octave really is, it's a 2-to-1 ratio, right? So as you heard, this A440, the A that is an octave down is A220, right? And the reason those sounds seem to blend so well together is because it represents a 2-to-1 ratio. So that means that if we were to graph that wave, the peak of every other wave would line up exactly, right? And that's not true of all these other possible relationships between pitches. I'm going to throw another term out at you, and that is an interval. An interval is a distance in pitch between two pitches. It's not really a distance. We always think in terms of space. What it really is a difference in frequency. There are many, many different intervals. And if you were in my music theory class, you'd have to learn them all. You have to be able to recognize them by ear, recognize them when you look at a piece of music. You're not going to need to know that for this class. By the way, you're not going to need to know how to read music or any of that. Right? That's not what the purpose of this class is. But you should know what an interval is. An interval is just a distance between any two different pitches, or a difference in frequency. The octave is one particular special interval. It's the interval that corresponds to a 2-to-1 ratio. There are other intervals that you're familiar with. You might not have realized that they are just ratios, but that's what they are. For example, the interval of a perfect fifth, like Star Wars, right? That interval we hear at the very beginning of Star Wars. If I play these two together, you can hear that they blend pretty well. They don't blend as well as the octave does. There's the octave, 2-to-1 ratio. Here's the perfect fifth. That's a 2-to-3 ratio, right? Or 3-to-2 ratio, depending on how you want to, right? This would be 2, that would be 3. They're a ratio, they're a relationship to each other. It's a simple ratio, and it produces a sound that blends well together, right? Lots of different ratios. You might have known already, actually, that music and math are deeply related to each other because, sound is caused by vibrations. We can measure those vibrations with numbers. We can establish relationships to each other, right, that might correspond to certain ratios, right? So as soon as you start studying music on a sort of basic scientific level, you immediately run into math. And this is why a historical figure that we're going to get to toward the end of this unit, Pythagoras. You all know Pythagoras as the guy who came up with the Pythagorean theorem, right? Describing right triangles, a squared plus b squared equals c squared. Pythagoras, who lived around the 6th century BC, is not only sort of the great-granddaddy of all mathematicians, he is also the great-granddaddy of all music theorists. And he saw music and math as being essentially two different sides of the same coin, or two different aspects of the same basic phenomenon in the universe. And he took it even farther than that. Pythagoras and his later followers, the Pythagoreans, were a sort of a cult, almost. Pythagoras was seen by his followers in subsequent generations for centuries, really. There were these Pythagorean brotherhoods and Pythagorean schools all over, let's say, Greece, Eastern Europe, the ancient world. And the Pythagoreans were kind of like a cult, and Pythagoras was kind of like their prophet figure. And this cult believed that the ultimate reality of the universe, sort of like the Force, since we're talking about Star Wars, the ultimate force in the universe was math/music. Two different aspects of the same thing. And that might seem like a kind of a weird idea, but it's not so weird the more you think about it. The more you think, for example, about the role of math in science, in describing the physical world around us. You can't do science without math. You can't really come to know the physical world without math, right? Now, I don't want to get too far off on a tangent. I'm just kind of like opening a door to your understanding of the relationship between numbers or math and music. So, intervals, differences in frequency between two different pitches, are hugely important in music. We're going to come back to them and talk to them later, but intervals just represent ratios, represent differences in frequency, which we can measure that difference precisely. A couple other terms in the book. I'm not going to go over absolutely everything in the book because you can read, and some of these terms are easier to understand than others. I'm going to focus on the things that you might need more help with, right? Not the things you might need less help with. So, for example, the concept of a pitch range. This is one of these words that's in bold print over here on page 5. The pitch range is the difference, or the distance, not really a distance, remember, between the highest note and the lowest note that a given instrument or voice can produce. So the piano, I said its pitch range begins at around, at this super low A, which is about 27.5 hertz, and the highest note way up here, that's the pitch range. Of course, we have different pitch ranges for different people too, right? We generally classify vocal pitch ranges into alto and soprano for women, and tenor and bass for men. Now, there are also some in-between ranges, which you'll read about. So, for example, there are women whose voices are not quite high enough to be soprano, but not quite low enough to be alto. We call them mezzo-soprano. Mezzo-soprano means literally medium soprano. There are men, that is adult men, whose voices have changed. There are men whose voices are not quite low enough to be considered bass, but not quite high enough to be really a tenor. We call them baritone. Baritone just means in between bass and tenor. If you join a choir, you will probably be, you probably wouldn't be labeled a mezzo-soprano or a baritone. Choirs traditionally are divided into just those 4 main groups. Soprano and alto for women, tenor and bass for men. And I keep on doing this high or low thing. It's unavoidable, right? Every time I do that, remember, there is no real high and low about it. It's not something that's occurring in space. It's something that's occurring in time. People with a higher voice are able to produce pitches that correspond to more vibrations, a greater number of vibrations in a given period of time. That's all that means. And people who have lower voices are able to produce sounds that have fewer vibrations in a given amount of time. One last thing. The pitch range of a given instrument is very often determined by its physical size. And you've probably noticed this. The larger instruments tend to produce lower pitches. Smaller instruments tend to produce higher pitches. Now that's completely different, remember, from the loud and soft. I'm going to talk about loud and soft next time. Loud and soft is a completely different issue. I'm just talking about high and low. Smaller objects tend to produce higher frequency sounds, all else being equal, and larger objects tend to produce lower frequency sounds. Why is that? Well, it has to do with, now this really does have to do with space, right? Think of a wave. Think of a sound wave which travels at a fixed speed. Now you might know that the speed of sound through air is something like 726 miles an hour, something like that. I might be off a little bit. It's 700 something miles an hour, the speed of sound in the air. Sound waves actually travel at different speeds in different materials. The speed of sound through a piece of wood, through a piece of metal, and there's some metal that just hit some wood when I dropped my glasses. The speed of sound through metal or wood is not the same as it is through air or water. In fact, different types of metal, different types of wood, sound will move at a different speed slightly. Now, but let's assume that we have two different pieces of metal. It's the same type of metal, or two different pieces of wood. Same type of wood, so whatever that speed of sound is through that medium, it's going to be the same speed, right? Whether we have a small piece of wood or a big piece of wood, the sound wave travels the same speed. The difference is, if we have a smaller piece of wood, this sound wave has less distance to travel, so it can make more trips back and forth in a given period of time. At the same speed, if we have a larger piece of wood, or metal, or whatever it is, that sound wave takes a longer time to make a round trip back and forth, right? The wave takes longer, therefore it occurs less frequently, therefore you have a lower frequency sound. And this, you'll see this, for example, when we look at the different families of instruments. So, for example, in the string family, you have the violin, the viola, the cello, the bass. They all look exactly the same, except the bass is big and the cello is still pretty big. The viola is a little smaller and the violin is the smallest, right? And that's exactly why we have those instruments in different sizes, so that we can produce different ranges. All other things being equal, smaller things will tend to produce higher pitch sounds when they vibrate, and larger things will produce lower pitch sounds. By the way, that's why you have that, when you look at a grand piano, you have that kind of mitten shape, right? The reason is the higher pitched sounds are over here with the shorter strings, right? The shorter strings are going to produce higher pitched sounds. And then as you get to the left hand, the pianist's left hand side, you have the longer string. So that's why you have to have that distinctive shape. It's the same shape you see in a harp, by the way. If you look at a picture of a harp, and there's pictures of all these instruments in the book, you can see this distinctive shape, and that's to give you different lengths of strings. Now, in the case of strings, there are other factors as well. There's the tension of the string. So, for example, you've all seen someone tunes a guitar. They turn this peg and they pluck the string and it goes like bang, 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 until they get the right pitch. So what they're doing is they are increasing the tension on the string. They are pulling the string tight. The tighter that string is, the less resistance there is to the sound wave going back and forth, and that wave can travel faster. Now, you have a hard time doing this with a piece of wood. It's hard to tighten a piece of wood, to stretch it. You need a lot of force. It's probably just going to break and not stretch. But with strings, you can increase the tension on them and get a higher pitch. Right? So even if you have two different strings of the same length, The string that is under higher tension will produce a higher pitch. The string under lower tension is going to produce a lower pitch. Now, I've got to wrap up this lecture, but you can see how complex even just the basics of sound is, okay? And that's why this class, even though it's intro to music, and even though it's a gen ed class, it's a 100 level class, you should not think of this as an easy class, I'm afraid. It's a difficult class because the subject matter is inherently difficult. I can't make it any easier than it is. It's just basically a difficult thing. And this is part of the beauty, though, of teaching about music, because you can teach about many different things at once. Music involves, as we've seen, it involves science. It involves understanding a bit about physics. It involves math. You will see very soon that it involves foreign languages. It involves learning about history and about culture, right? So we're going to do all of those things and hopefully enjoy ourselves a little bit as we do. So if you have any questions about frequency, about pitch, feel free to ask. Remember, as I'm going through and doing these lectures, I'm not just going to read verbatim out of the book. I'm going to use the book as sort of a point of departure. I'm going to touch on things that are in the book. But the book is there for you to read, and I'm here to try and explain stuff in my own way. And I will focus on the things that are probably more difficult to understand it, need more explanation, and I might not necessarily touch on other things. Next time we will talk about dynamics, which is volume, the loud and soft aspect of sound. See you then.